Thank you very much. Well, I had to start thanks a lot to the organizers for organizing this beautiful workshop near Mount Fuji, and for inviting me, of course. I mean, I'm pretty much enjoying all the talks and the place. So you can hear me at the back, or yeah, okay, good, yeah, perfect. Hopefully my voice keeps like this. So what I'm going to talk about is very related to Kentaro's talk. So it's about B-brane transport in some non-abelian models, but different from the ones Kentaro studied or presented. In a sense, they are harder, but in a sense, they are easier, much easier, actually. So this is, I should mention, this is joint work with my student Van Lin. It's in progress, so there are still some mysteries and some open questions you will see. I mean, okay, so first maybe I will use this Blackboard to fix just my notation, since Kentaro already did it. I will just kind of repeat this. So for me, gauge linear sigma model will be characterized by a quadruplet of things, which are the gauge group. We're going to fix it later. We have the matter representation, which I wrote like rho m for matter. So it's the representation of the matter, or chiral multiplets for physicists. So in some complex vector space. And we have our superpotential, which is something here. It's a polynomial, it's a function on the coordinates of B, so it's dual, and it's G invariant. And there is also the R charge, but I think I'm not going to use the R charge at all. So this is just in case you are a physicist, is the vector R charge. And all these things have to satisfy several conditions. Just the only condition I'm going to remind you is just in order to have Calabi-Yau type GLSMs where all these things works nicely. I mean, things works also nicely on non-Calabi-Yau, but it's different. But so in order for this to be Calabi-Yau, rho m. So Calabi-Yau condition, I will remind you, is rho m factors through SLB. Okay, that's it. So all the examples are going to satisfy this. You don't have to double check it, or if you want, you can. If you are very bored, but okay, that's one thing. And in this GLSMs, we will be also concerned with B-branes. So I guess maybe I can fit here B-branes. So B-branes also make a lot of they appear a lot on the previous talk. So let me just write for me what are going to be B-branes. So B-branes comes. You can describe them as a triplet of objects. So that I will call T, maybe rho sub m and R sub m. So what are these things? So the important one here, so all these objects are, all these triplets, you can think of them as a single object that sometimes, because it's B-brane, I will call it calligraphic B. And they belong to a category that's called the category of matrix factorizations, or G equivariant matrix factorizations of the superpotential W. So maybe the thing I had to remind you, so I wanted to use one Blackboard for that. Maybe here I can, maybe the thing I can remind you is that T square, so T is a function, T is a function of the coordinates of V, so T you can say is an odd endomorphism. Is an odd endomorphism of some space that you call M. That's where these M's here come from. So M is a Z2 graded vector space. All right, Z2 graded vector space. And actually, this M0 and M1, these are free symmetric B-dual modules. Okay, so that means, in other words, T is like a matrix with entries that are functions of the coordinates on this vector space. So the condition for T, okay, I didn't manage to fit the condition for T there, I will fit it here. But the condition for T is that T squared equals to W times the identity in M. And I hope I'm writing big enough, or I'm writing too small. Yeah, up to that there. Up to there is big enough, I think, okay? Don't worry, I will write larger, but okay, so that's the condition. And rho M and Rm are, I will only say that they are compatible with rho little m and what I call R. So these are representations again of these the R charge, which is just some C star action, and rho m is a representation also. Rho m is also a representation of the gauge group, but now is here on GLM. Okay. So I think, I hope I didn't go too fast. So this is my super quick introduction to GLSMs and B-branes on GLSMs. Okay, so anything, please stop and ask me if you didn't catch it. Or all right. So the main thing is, yes, I did this because I need the notation. So what we are going to talk now is about a particular type of, as I mentioned, of GLSMs. And in the same spirit as Kentaro's talk, we are interested in GLSMs where one of the phases, as physicists call it, or if you want, one of the chambers on the 5-parameter space describes some nice geometry. And the geometry now I'm going to talk about the geometry I want to analyze. So previously the geometry was this Pfaffian, Grassmannian, Calabi-Yaus. Now I'm going to talk about something called determinantal varieties, which is something which is something very general, but I'm going to work on a very specific one. So you will see it's very concrete, very concrete. So what are determinantal varieties? So the GLSMs I'm going to present, and all this was studied long ago in a paper by Jokers, Kumar, Lapan, many people, Morrison, and me, 2012. Actually, I finished this paper and other related kind of when I first moved to Japan, to IPMU. That was one of the first talks I gave, was about these things. So now I'm back to Japan after many years. I'm talking again about this, and actually I found a mistake on them. But it's a very subtle mistake. It's a very subtle. You wouldn't have found it. Okay, I will tell you actually. It's very subtle. So what are these determinantal varieties? Okay. So in a nutshell, we take two vector bundles, two holomorphic vector bundles over some space V. So this space V is going to be smooth and compact. Eventually, it's going to be just projective space. And these are vector bundles, holomorphic vector bundles. Of course, we do everything holomorphic. And for the sake of this talk also, I'm going to simplify a lot these things. So First of all, I'm going to take them both of the same rank n. So then you take a section of home E to F. So again, it's kind of like a matrix. For physicists, it's just a matrix with entries, functions, and you define this guy. You define this guy, which is the points in B, such that the rank of A of phi is less or equal than K. And that's it. That's an algebraic variety. It's in general not a complete intersection, but it's an algebraic variety, and that's the determinantal variety. Why? Because this condition is given in terms of determinants of minors, right? So that's the name come from. So one thing is this variety is highly singular in general. It has a huge amount of singularities, which are, if you want, the singular loci, the singularities inside this variety are all the points where the rank drops k minus 1. So it's huge in general. In general, this will be very big sub-variety, and the singularities are here. In principle, there can be also singularities in B, but I assume B is smooth, so I'm away from those. So if you try to put this into GLSM, it's pretty hard. I mean, you will have a hard time because it's singular, or very singular in general. But you can do something that was not like our idea, but there exists a resolution of this type of varieties that was invented, I think, by Harris. You can go to undergrad books in algebraic geometry, and actually you can find this resolution, but somehow, for some reason, many people are not familiar that I have talked. Maybe all of you are familiar, but that's okay. I will repeat it anyway. So I will call it XA, because this XA is going to appear a lot. And the resolution, you do the following. You do the following. So you define a variety that you call BE, L, and BE, L is the relative Grassmannian. Is a variety whose fibers are this G. Why put K? Sorry, I'll call it L. L. So it's a variety whose fibers are this relative Grassmannian, and the base of this is simply B. So this is pi. So you just define this guy, and here what you do is you take the points. Now I'm going to call them P. The point in B, E, comma, n minus k, and then A at pi of P acting on pi so just to explain, so this pi of P is a point again in B, and fiber over P is a point. It will be a point in this kind of relative, in this Grassmannian. So it will be a L-dimensional, in this case, an L-dimensional subspace of this vector bundle. So that what it means is that you want that the fibers are spanned by the kernel of this. So you can check that this thing, every time this matrix drops rank, you get kind of a higher dimensional thing here. So it's like a generalization of a blow up. So let me write for you a simpler. This is maybe a little bit too abstract, so I will write a simpler case. So I will write it here. So So this will clarify probably that construction. So we consider the case. So we are going to consider a very simple case, which is L is some line bundle tensor O of B, let's say, to the n. Then actually this B E comma n minus k becomes just B becomes a trivial bundle. This is something you can check. Grassmannian. This becomes like this. So you don't have to think about this more abstract situation. So in this case, it becomes like this. You can still keep f arbitrary, but we are going to fix f. So then you can write, if you want, you can write xa has points like this. So you can write them like this in this b times g n minus k. And where a of phi acting on x is 0. So it's just the pair of points where, so remember, x is a point here, so it's x represents an n minus k subspace. So is the points where this happens. So if a of phi is of rank k, there is essentially no one unique point here. Only the subspace of dimension n minus k is spanned by the kernel. But if this drops rank, you have more points here. Your subspace grows. So you have more points on the Grassmannian. So that's the idea behind this resolution. Okay, so I hope that was more or less clear. You can ask or complain. Okay. Okay, so the idea is to study, as I said, a GLSM that realizes this has one of these phases. So the GLSM I'm going to consider, so we are going to consider this GLSM. I can call it informally GLSM for XA. So again, I have to specify all those things. So I'm going to limit myself to the case B is the projective space. So I promise I'm going to do something really trivial. Epsilon is going to be O to the n. I mean, really trivial in comparison with this super general setting. But this is going to give us very interesting varieties, of course. Otherwise, what's the point, right? And this actually, I'm going to take it like this. That's it. Very down to earth. So the GLSM that you can consider is the following. So you have gauge group U2 times U1. And let me write the matter representation. So I will write it in kind of this physics style. It's exactly equivalent to the way Kentaro wrote it, but I like it this way. So, sorry. In principle, the n minus k. Sorry, n minus k. So these indices here represent some copies of the representations I'm going to write down here. So this, for example, this phi a, you take it on a representation of weight 1, and here a trivial representation of this group. And this p, you take it with weight -1 under U1, and a representation, fundamental representation. So this means fundamental, or rank or representation of n minus k, the defining representation if you want. And this xi, you take it with weight 0 and the anti-fundamental, meaning, right? So if I take element g here, you act with g, this act with g to the 0, so trivial g and g to the minus 1. Yes. And this act with this weight. Okay, so I should write that. Of course, you can specify, well, in order to specify the R charge, I need to talk about the superpotential. So I'm going to give you the superpotential. So the superpotential is going to be the following.
So how many A's?
Very, very good. I is, so I need n copies of these two. Little n copies, and this other guy I need a in principle is 1 to, I think this is n times n minus k. I think that's the, let me see, if this is 4, 2, 4 minus 2 is 2. 4, 8. Yeah, it works. Yeah, that.
How is it like R, D equal to R?
R is I'm sorry. Yeah, R is. These are going to be there. Yeah, I just put this R there. Yeah, so everything is n and k now. Very good. Thanks. Potential. So I have to do the following. So the matrix A is still there. So I specify, remember I want to describe this variety. So I take your matrix A. You take the matrix A. So got the matrix A. I will write it like this. Right. I, J. Pi xj, and to make it gauge invariant, okay, let me just to clarify this a phi, which is has a matrix, is a matrix of n times n. No symmetric, nor anti-symmetric. In this example, entries, its entries are linear in phi. Okay, in this example, if you that's because of I choose this. If I choose other bundles, your entries are going to be different. But here is so it's an n by n matrix. Now everything is vector spaces because I'm working on the GLSM, so there's no geometry here. So everything is just vector space. So I can say safely I take some matrix n by n, and with entries linear in phi. And of course, there's no condition on being symmetric or anti-symmetric. It's just arbitrary in that sense, but also the complex structure of this space is going to be determined by, of course, by the coefficients of this matrix. So which linear forms I choose has entries. So I want to satisfy A, satisfy some genericity condition in order to guarantee that I'm not at a point where this XA becomes singular. All right, you don't want to do kind of a dumb thing like choosing A equal to 0 or something like that, right? So there's some genericity condition on this A. And this is the potential, and you can read the R charge from there, but since I'm not going to use the R charge, I'm not going to go into that details. So these models you can find on that 2012 paper. They can be generalized, maybe not we didn't analyze the most general ones, but these ones are good enough for us now, and are good, well, they had been good enough for the upcoming paper. So these models, they have to say on the paper, we call them PAX models because the superpotential look like PAX. It's not a name I'm proud, but just in case, kind of a history of names of these things. Okay, so in order to show you, okay, I had to say a few things before I go even more specific. Let me check my time, how am I doing? I have until 10:45, right? Yeah, I think so. 10:45 or 1:45, I don't know. Okay, very good. So the important thing I want to say about this model is that it talk about the so-called phase space. Phase space in the sense of physics. In the exams of Kentaro, what's the phase space? The phase space is how this theory behaves as I vary the phi theta parameters. Okay, so the phi theta parameters, if I want to say it in just one phrase, to say it quickly, parameters that lives on the center of the Lie algebra of this. Okay, so I have, and they are good to, they will help me to specify some symplectic quotients that will be related to this representation. So there's two, in this case, there's two phi theta parameters, different from the case of Kentaro where there was one only, because there it was group just, its group was like UK, so there was one phi theta parameter associated to this that I'm going to denote like this. So it's a complex number. It's a complex number associated to this, and there is a complex number associated to this. If you have like no idea what I'm talking about, but you should from the previous talk, or maybe you didn't know even on the previous talk, you can say, so if you have a representation of a Lie group, so you have a moment map associated to these representations. So these phi parameters are level sets for this moment map, for the moment map of U1 and for the moment map of Un minus k. So that's one way to understand if you are not familiar with this. So I have a moment map and I have a variety associated with these moment maps. So what I'm going to compute, so the kind of what we can call the Higgs branch, physicists will call the Higgs branch. So there is a moment map. So this is, hopefully you can see, or it's kind of hidden, but a moment map. This is the moment map associated to the representation, this whole thing, okay? So you just take mu minus 1 of theta 0, comma theta 1, and then you take the quotient by G. So this is a symplectic quotient, and you intersect with the critical points of W. So that will be what we will call the classical Higgs branch in physics. In examples like the one Kentaro show us, classical Higgs branch in one phase, in this so-called strongly coupled phase, it's very nasty. It's not a nice variety. So you have to do a deeper analysis of your theory to understand what's happened with the dynamics there, if it's a sigma model or what it is. Happily, in this example, in this set of examples, all the phases are weakly coupled, which means if you just compute this classical Higgs branch, you will always get a smooth, compact variety. And the theory on that phase will be a sigma model with target space such variety. So let me wrote, I had colors, so okay. So let me, usually if we project to this space, so we have this space, R2, and you ask, okay, how this quotient behave? Because of course there are choices for this, where this moment map has some unstable loci, and this variety is very singular. So classically, what you get is that in most of these, when you vary these parameters, is smooth, but there's some loci here. Good. This one. Yeah. So there is like some sub loci that just look like this. There's possibly another one, but in my examples there are none. Okay. So in examples is something like this. So these red lines, this quotient is ill-defined. Okay. So those are the places that eventually are going to lift to asymptotically to places where the theory is ill-defined. So you don't want to touch that. So away from that, here this quotient, this x Higgs, what I'm writing here, this x Higgs is going to look exactly, if you choose them like this in this chamber, if you want, it's going to look like XA. If you choose them here, it's going to look like XA transpose. The same thing, but with the transpose matrix. And here it's going to look to another variety that I'm going to call YA. Okay, so I don't want to waste much time describing YA, even though it's very simple. It's also some other kind of resolution of a determinantal variety, but I will leave it. I will leave it like that because what I'm going to focus now is not on YA, but I'm going to give you some results about the crossing of the brane transport along this. I want to study these monodromies. I'm going to keep my base point here, in order not to have to introduce much more notation. So, if you remember that Kentaro has this picture where you have the cylinder with several points removed, and you have the monodromies. So here you want to do exactly the same thing, but now it's a 2D, right? So your monodromy had to surround kind of some component of the discriminant here. So this, as I mentioned, this red thing is what we can call the classical discriminant. I will put quotation because I don't know if it's standard name. So if you are a physicist, you know that that's not complete. That's not very correct. In the same way that in the picture of Kentaro, you have these 3 singular points. If you do classical analysis like that, you may imagine there is only 1 point, for example. Okay, so the quantum version of that discriminant is actually much more complicated. It's it's going to be some curves inside this space, inside the T space, rather than just some lines in zeta. So what we learned from Witten is, first, in order to do the correct physical analysis, and in order to do this, because this you can complain immediately that I'm not going to be able to do this in R2. How can I go around? But the idea is that these loops really are in T space, okay? So that's what we learned from Ed many years ago, that you have to consider these are the actual physical relevant couplings, so your space really has to be enhanced or lift to C2. Yes, to C2. And there, your discriminant will be codimension 1, and you can go around. So okay, so in order to be more concrete, let's see. Yeah, okay, all good. We're going to consider examples. So examples. In order to talk about the quantum discriminant, I need to go to examples. So that I cannot do. I mean, in general, I can say things, but again, it's too abstract to present something useful. So examples. So these are both Calabi-Yau threefolds, and the examples are k, n equal to 4, 5. These are two examples that are very interesting, and the other is k, n equal 2, 4. So let me say something about this, so you don't have to compute them, but maybe you are very fast and it's still there. Here XA lives in P4 cross P4. It's a threefold here, and this one was studied by, actually this one was studied by Hosono, by and Takagi. So this is also, you can call it determinantal quintic. So if you define a quintic has the determinantal variety, generically it has some singularities where the rank drop again, and if you resolve it, you get something like this. So I also can call it Hosono-Takagi model, but there was already Hosono-Takagi model in the previous talk, so I would just call it the abelian model. So it's abelian. So you can check the gauge group here is just U1 times U1. This is the non-abelian model, where XA is embedded into is a subvariety of P7 times G24. So this we call it the GM model in our paper. GM model because GN two Scandinavian mathematicians, Gulliksen and Negard, that studied many years ago the resolution of the ideal defining this thing. So yeah, and again some piece of history. Yeah, please.
So just the numbers. So R, what is R? That's R.
It doesn't match. Hopefully it matches. I say it by heart. Yeah, it's fine.
So it's the
Yeah.
first P has dimension R.
Yeah, it's P4. Yeah. Okay. Arithmetic is very complicated. All right, so these are the two examples I want to focus on. I kind of wanted to mention what is so special about computing in the monodromy or the great restriction rules in these two examples. Okay, so now that I put the examples here, I can tell you what is the quantum, what I will call the quantum phase space. So as opposite, when I said maybe this one, we can call it, this one is the classical phase space. Okay. So quantum phase space, I cannot draw it because quantum, as I mentioned, you have to lift it to T space, so it lives in C2. But I can. So there's two things that happen in this case. One is that you have to consider it in C2, and the second thing that happens is that you have to replace this red thing, this kind of red collection of lines or red, I don't know how to call it, fan, by some curves. By some curves that actually asymptotically they will look like this. So there will be some curves that when projected to the real, it will be some curves that maybe will do something complicated here, but asymptotically will go like this. So this is kind of the quantum. So the curves actually are computed because physicists know how to compute them. You can compute them if you are a mathematician, if you have the mirror, for example, of your Calabi-Yau. Well, that's one way. I don't know if there are other ways. But if you have the mirror, like in the case of Rotland, you can compute and get the discriminant like these 3 singular points. You only get them if you do some, as I said, some quantum analysis. This classical, no. So in this case, you have a mirror, also analyzed by Shinobu and Hiromichi. But the mirror here you can compute, and you can compute this quantum discriminant, like this black, sometimes called amoeba. But in this case, you have no mirror available. There's no geometric mirror, at least in this example that I'm aware. So the only way to get it is by physics. So let me give you the properties that I need for this quantum phase space. I'm not going to draw the whole thing. What I need is the following. So here, let's say you have XA phase, and I will write 2 divisors that are very useful. I hope it's visible. So this will be the divisor I will call Z equal to 0. It's not very good. So this divisor I will call Z equal to 0, where Z is e to the minus t0. This is the projection in the real, right? And this one is going to be W equal, you can guess what it is, e to the t1 now without the minus equal to 0. So these are the 2 divisors, and this is the phase. And the quantum version of that discriminant will be a curve that I will write schematically like this, like this, and I will call it delta. So this is the curve that's going to replace those red lines. And the important thing is here, this and this, they intersect at one point. And here they also intersect at one point. The intersection is highly non-transverse, if you are curious. This delta will be some curve of degree 5 in this example, and this point will be one point of multiplicity 5 in both cases. And in the non-abelian version, you have a similar picture that I want to draw, but with a difference. That's a lot of exercise too. Okay. Yeah. So in the non-abelian version, I'm writing just this quadrant because I mentioned that's where I want to focus myself. And you have again these 2 lines. Let's not. Well, with a lot of imagination you can see them, but okay, maybe. Okay, now you don't need imagination. These 2 are exactly the same definition, and now you have something like this that I'm calling delta 2, that also intersect at one point here and a point here, and why it's called delta 2 because there is a delta 1, right? So there is a delta 1 that I don't know, let's use another color. So there is another one that I will write also kind of okay. I should have to leave it like this. So, okay. So there is some other one that I'm going to call delta 1. Yeah, let's not mess up this picture much. But so this delta 1 and delta 2 are curves of different degrees. So actually, I put it here. This delta 1 is of degree, if you are curious, these are degree 4, and this is degree 8. They are written explicitly, but yeah, I mean, I want to finish the talk at some point, right? So I'm not going to write it. It's long, yeah, it's a nasty, it's kind of an ugly formula, but and now it comes the revelation. I mean, in a sense, if you are curious, the mistake was in these deltas in the paper. The reason, for the people that know, is that we ignore the W bosons. So the way we compute the discriminant, there's something missing. But what changed is a sign, just a sign on one of the variables of these polynomials. But I were unable to detect it, even though we wrote 2 papers about them, until now when I wrote this paper about the grade restriction rule. All right, so very important thing, very important, is to say here again, these two, the two, if you intersect with this line, is again 1 point. And here there is again 1 point. Okay, 1 point. So, all right, very good. So, if you look, without entering into too many details, if you look locally here, let's say you restrict to this red plane. If you restrict to this red plane, right? So let's write it like this, very schematically. This thing here, if this red plane is exactly at infinity, it looks like there is a singular point here, and what you are doing is kind of some monodromy around this. And the same thing will happen here if you restrict kind of to this red plane, but kind of very, very schematically, as I said. So the questions you can ask now is, what is the grade restriction rule for x and y crossings? So what I call x and y crossing, so I still have this picture, so I will call this one here, I will call y crossing, because it goes from x to this thing I call y, and this one I will call x crossing. Okay, now this is getting very messy, but hope you get the idea. Or I could have done it like this. Here there is x crossing, and here there is y crossing. So you need to find one question you can ask yourself is to get what's the grade restriction rule to transport brane from here to here, or from here to here. Of course, you could have chosen any other wall, but I just choose this one to present it to you. And because the other ones are going to be pretty much analogous. So the reason I talk about this is because intuitively you will have at each of these crossings you will have one restriction on your weights of rho m in the way that Kentaro presented. Oops. Like in Kentaro's example, you have multiple points here, so you have multiple paths. But here there's only 1 point. So that you have to believe me, because I didn't give you the deltas. But here there's only 1 point, so you expect one window. Very good. And you expect 1 point, and you have one window. That's right. So so I can give you the answer, because those windows are actually not so difficult to describe. So window categories. So let me describe them. So let me give you the first result. So it's not so difficult to get to this result. So at y, maybe I should write it y of theta sub 0 is defined. So this will be defined. So rho m with u1 weight, q0 with u1 weight, q0 we do one weight q is such that here I write it in general. Theta 0. So this is what you get on that one. Very good. How Wx of theta 1, right? So Wx is moving in what I erase it, but this is the one direction, this is the 0 direction, okay? So this is a subcategory if you want. This is a subcategory of MF G of W. And
Sorry, what do you mean by
yeah.
weights?
In the gauge group. So my gauge group now is U1. Sorry, this one has two U1s. I'm really sorry. So my gauge group is now like this. So let's call this one 0 and this one 1. So band restriction rule. I should call it band restriction rule. So it's a subcategory of that. It's bigger still. It's bigger than the derived category of XA. But that's not a problem. And here rho m is still there if you so you shouldn't ask what is rho m at least. Un minus k with weight q alpha, yeah, q alpha. So alpha is 1 to n minus k alpha, such that this. Okay, so this one for all alpha. So it's some kind of a cube, hypercube, or square. In the example, it's just square or some interval. So if you restrict, so of course this also here. So if you restrict your representations of those B-branes to the representations rho m that are compatible with the rho small m, but satisfying in addition this condition, then that means those B-branes can be mapped one-to-one from this phase to this phase, or from this phase to this phase, depending which one you are crossing, depends which one you choose. Okay. So getting those. Let me see my time. Getting those gray restriction rules, if you are more or less familiar with this, is not that difficult. But here is the interesting thing. So let's say I will just give you one of them, okay? So so you can compute explicitly. So for GN model, you can compute explicitly Tx and Ty. Tx and Ty will be the autoequivalence associated with going around the x. So here is like Tx, and here is like Ty. So what we found in the case of Tx is that this is something like this. OXA. No, wait. Yes. I think. Tx. I think is this one. -4. Where this means twist by that of Sx to the -1. And Ty is something that we have the matrix, but we don't have a nice expression like this. Okay, but Ty maybe doesn't have. Oops, but you can compute in both cases. You can compute the monodromy matrices, acting on a nice basis of your choice. But we choose a particular basis, and we can compute the monodromy matrices in both cases. And in this case, you can also see it, of course, matches with this. This one is a bit more complicated. We don't have a nice expression, but we still have one expression here for this one in the following way. So how you can get a better expression here? So you can take which one this was? Ty. So you can go around this point. So you go around this point, around the intersection point here, and you put a 3 sphere. So you go and here you put S3 epsilon. So S3 epsilon is a small sphere of radius epsilon, center at the intersection point. So why I'm doing that? If you do that, this is something that actually has been well proposed in some very old papers for abelian models. So if you do that, the intersection of this S3 is epsilon 3 with delta and S3 epsilon with the, in this case I call that one W equal to 0. These are going to be lines. So if you look inside that sphere, inside that S3, these intersections are going to be real one-dimensional lines. So they're going to be links. So here is, okay, I had to at least say this to use my picture, my secret picture here. So if you look what's going on, you will find that this is how it looks like. So it looks like it looks like this. So you have that this red one is the W equal to 0 divisor. This one is the delta 2. When I said they are this, it means this intersected with the 3 sphere. So around there it looks like this, like some linked some link, where each link component is associated with one divisor. So the monodromy path going like from one direction to the other, from XA and back, going through the Y boundary, is something that follows kind of this red line. It's something that goes kind of like this. And then back. So this is like the monodromy path. So using basic knowledge of fundamental group of link, you can decompose this monodromy path in generators of the fundamental group of this link. So the generators you can choose are this one, and this one. When I wrote that arrow, I meant like with some point outside, like some point here that goes like this. So you have this tree, and you can decompose this line. Sorry, I'm over time. Okay, with this I'm going to give you the result. So with this I finish. Okay, if you decompose the path associated to the monodromy into the generators of the fundamental group of that link, you can actually express this Ty as a composition of simpler functors or simpler autoequivalences associated to each of the components of the link. That requires, in some cases, you can do it almost unambiguously. In this case, I present it requires a little bit of guessing. So I will just give you the answer here, and this is the end of this. So the answer is this. If you decompose it. How you can check this is at least slightly correct? Well, you just compare the matrices. You just compare the monodromy matrices, and if you well, all of them are XA. Okay. This is this one. So that's the proposal for the monodromy around. That's the proposal for this in terms of some more basic autoequivalence. Okay, I finished here. Thanks for your patience.
さっきフォーダナイスをアゼアニックエーションコンポーネンツ
How is this related to this picture?
I'm sorry. Yeah. That was super fast. It's just link, kind of link. Let me see if I even wrote it. I think here. Yeah, it's just link fundamental group of this link. So you have to think of this. This is like inside S3 epsilon. That's center at that intersection. This is how this is really, when I said delta 2, is like delta 2 intersected with this S3 epsilon. So it's a real line. So this and this same thing here. So let's say your monodromy path is kind of going like this, right? So this is, I don't know how we can call the monodromy path. You can call it T of monodromy. It has a loop. So you want to decompose that loop into other loops where you have a hope to guess what is the functor or what is the autoequivalence associated to that loop. So for example, let's say this loop, this one. So this one means like this, around this. So this is this one. So you know that this one is some tensor product, right? This is like the boundary. So this is like 0 minus 1. This one, there's one of them that is kind of very clearly T of OX. Maybe I'm messing it up. And the other one, you just have to guess it. So, so then you just write this monodromy path in terms of all these other, using just fundamental kind of results on pi 1 of the link complement. So you will have that this Tm is some kind of something like, if we call this B, and if we call this, I call this A2, and I call this one here A1, you can actually decompose this only on them. Like, so you will think like V to the minus 3, A2, B3, etc., etc. So you will get a decomposition in them. So then your only job is to guess what are these. So of course, I don't know any way to compute independently the monodromy around like just one of them, except for this one. But like just around like one of these or the other. So but if you kind of guess it, you can get that formula. The only checking I have is that if you compute the monodromy matrix using those windows, and you compute the independent monodromy matrices of all those functors, all those autoequivalences, that multiplication actually gives you the same. Yeah.
So I know you said you didn't want to talk about phase Y.
That's okay. Yeah, I don't want to.
So that's like sounds nasty.
No. It's okay. I just didn't want to. I can write it for you. I mean, I have it somewhere. It's yeah. It's really simple. No, it's really simple. It's just. It's like this equation. So this is an equation just in P and X.
And that U gauge group is acting on the fibers or not?
Yeah, the non-abelian one acts here and also acts on the fibers. Yeah, that's right. And the abelian one, that's why there is this projectivization of this. And the phi is just gone.
So might it be that this T is corresponding to like the structure of anti-branes here in some way? I mean, is there something?
Yeah, that's how it's supposed to be. But the thing is, I only have one point to study, which is it's a very, very bad point in a sense. It's a very high multiplicity. So if you go to the mirror, that will mean that point the divisors there will intersect non-transversely. Then if you want to compute the monodromy of the periods around that point, you have to resolve it and get many exceptional divisors.
But you said if you go away from that point, you have these complicated.
Yeah, that's right. That's right.
You can do that.
I can do that. Yeah. So
the great restriction rule for along this, away from this point.
Yeah. So I said if you had this kind of W equal to 0 plane and you have like this point, if you move a little bit, this is going to be like this, which are exactly this.
There you can.
But how I do this? I don't know how to do it. I don't know which model to use to do that.
So
Like what?
You have the model.
Yeah, but which model I used to? So the way I got the restriction at this point, maybe you know, maybe you can give me the answer. But the way I got the restriction is because if I am at W equal to 0, I can consider like a local model where essentially I remove everything that's charged under the Otto gauge group or something like that. There's some obvious local model I can use, and then I can derive those windows. But if I move a little bit, I wouldn't know like which I need a one parameter model again, right? That will have these 3 singular points. And I don't know how to derive that one parameter model.
That's what you mean.
Yeah, maybe you know. I didn't saw about this very much, but yeah, that will be really nice. So because that I will be able to check if this guess is true.
Any other question or comments? If not, let's thank speaker again.